locks and synchronization between threads, right? Because you would have some piece of code which are critical, which are basically critical sections, and you cannot afford to have multiple threads modify those critical sections at the same time, right? And similarly, you would need some way to communicate between multiple threads. You may have a worker thread and a master thread, and when the worker thread is done, it should notify the master thread that with the result of the calculation, right? And finally, you would have to deal with exceptions. So Haskell, though most of the code you would write will be pure, and there hopefully won't be any exceptions or errors in that code. But when you're working with real world examples, you have to deal with exceptions like, network is out, or disk is full, or and your code has to deal with them, right? And finally, transactions. So sometimes in your code you would have cases where you want to modify multiple things, multiple variables in a single atomic transaction, right? So that the effect is visible all at once. So Haskell provides great tools to deal with all of these. So we're going to look at them. First of all, I assume that people are familiar with Haskell here, because I'm not going to talk about the syntax or the libraries or how to structure code and such. I'm just going to directly jump into the concurrency tools it provides. So this is what we're going to do to demonstrate the tools. We're going to write a multi-user chat, right? A chat server is a typical example of a concurrent program, and we'll see how we do that. The features we're going to have are very sparse. We're just going to have a bunch of users. It should be able to users should be able to log into the chat server and talk among each other like private messages, which is what I call message here. And then there'll be channels in the server in which multiple users can join and then talk in the channel. So when you talk in the channel, everyone else who is following that channel or is in the channel gets a notification, right? So which I called a tell, right? So that's all. We're going to have only 2 features, and this is the plan. First thing we're going to do is add the ability to accept the user's connections, right? So you should be the server should be able to accept the user connections and keep it open as long as the user is connected. Then we're going to add user to user chat. Then hopefully if we have time, we're going to look into user quitting and user just going away, becoming inactive, how to deal with that. And then we're going to implement channels, leaving, joining channels, and chatting in the channels, right? So this is going to be sort of a little like a whirlwind tour, because there's a lot of ground to cover. So hopefully we'll finish it in time. So let's start. So first thing you do when you write any Haskell program is to write down the types that you require in your system, right? So for this very simple, the very first feature, the letting the user connect to a server, we just need these 3 simple types. There is a user, who is identified just by the username, which is a string, and then there is a client, right? A client is basically a representation of the user on the server. So a client contains a user, a client user, and a handle, right? So if you're familiar with Haskell, a handle is somewhat like this, represents the socket to which the user is connected to, right? So a client is a user and the user's handle. And then finally there's a server. The server is, ignore the Mbar, but you can see that server is a map of user to user's clients. That's all. So every time you add a new user, you add that user to the client, to the map, and when the user goes away or quits, then you remove the user from the client. What's interesting here is Mbar, right? So let's see how. So we have the types ready. This is okay. So we have the types ready. Let's see if we can write the code which accepts the connection, right? So that's it. The run server function, it takes a port and starts up a server, right? So if you're familiar with server sockets, it basically listens. So every time someone connects to that socket, the server socket, it accepts the connection and on a different port, and then basically runs calls this connect client with this code. So there are a few interesting things here. First, let's get rid of that finally. So finally is somewhat like a try finally if you're familiar with Java. It basically means that run this thing, this function, and when it is done, run that other function. Do cleanups, right? So it's pretty simple. Just when the connect client is over, the client is gone, then just close the handle. Just clean up the resource, right? Another interesting thing is the fork IO at the beginning, right? So that's the interesting part here. So you can imagine that since there is a forever there, that means that the server will keep looking for new connections like all the time. But you can't talk to the client in the same thread, the same server's main thread, right? Because that would block the server's thread. So what server does is that whenever a client connects to the server, it forks a new thread. That's what fork IO does here. It forks a new thread, right? It's very similar to fork from other languages. So let's see what threads are in Haskell. Threads in Haskell are a little different from, if you're familiar with threads in Java, they're different from that. The threads in Haskell are green threads, right? That means that the threads are managed by the runtime. They are not managed by the OS, right? So the runtime would manage your bunch of green threads and map them onto a thread pool, an OS threads pool, which is which are the actual OS threads. So that's one thing, and that means, and the second thing is the threads are really efficient, memory efficient. If I'm not wrong, each thread takes like 32 KB of space. So it's very cheap in terms of memory, right? The third thing is non-blocking IO. All IO in Haskell is non-blocking. The Haskell's runtime manager, the IO manager, as soon as you do an IO call, which it sort of suspends your green thread right there and waits till the IO call is finished. It's very much similar to an event loop in Node, for example. In Node, you would give a callback explicitly when the IO is done. In Haskell, you don't have to do that. The runtime will suspend and resume your threads automatically when your calls are done. The IO calls are finished doing whatever they're doing. Then it resumes the thread automatically at that position, right? So when the IO manager suspends the green thread, the OS thread on which the green thread was running gets free and is ready to be used by some other green thread. So the code looks threaded, you write it as a threaded code, but it's efficient as evented code because it automatically in the IO manager it becomes evented automatically, right? So these two things combined, the non-blocking IO and the memory efficient structure of codes, means that you can launch hundreds of thousands of threads, even possibly millions of threads in a single Haskell process, right? And they would all map to a small bunch of OS threads and they will all run fine, and the runtime will automatically manage the suspension and resuming of threads, right, when you do IO. So that means that you can launch threads even for like smallest things. You want to write a timer, you can launch a thread for every timer, right? You want to do a HTTP call, you can launch a new thread for every HTTP call. You don't have to worry about thread pools, you don't have to worry about a lot of other things which you have to worry about in, say, Java, right? So the how do you enable threading is you give this -threaded, the -threaded option when you're compiling your code, and then Haskell runtime, the threaded runtime will be included in your program and have an option to automatically have green threads, right? And you can specify the number of cores you want to run on when you're actually running the program. There's a runtime option for that. So that's what threads are. That's what fork IO does. It launches a green thread which is very efficient, right? So the next thing to look at is Mbar. So if you remember the server users here in the code, it's inside an Mbar. Yes. So the Haskell, the IO manager already does the scheduling like it does the scheduling for green threads. It's pretty good at it. It uses the OS's native support for evented IO, and it works pretty nice. So it will use the OS's native event like event loop, event poll loops, and event loops and such. So it will probably be the same guarantee that you would get from. I'm not sure about ePoll and such. So it will be the same guarantees. Can I take the questions after the thing? This sort of to cover a lot of things. So we saw that the maps, there's a map of users, map of clients kept in server, which is wrapped in an Mbar. So Mbar is nothing but a mutable variable. It's short for mutable variable, right? So you cannot change variables in Haskell. There are no variables as such in Haskell. They are called bindings. Once you assign a value to a name, that's it forever, right? But you do need to change variables sometimes. So that's why you have mvars, right? So mvar is sort of a container for it's a container. It's like atoms in closure. If you're familiar with, sort of like atom in closure. So you can think of mvar as a box, right? So you can put some value inside it. You can get the value. You can change the value and such. Very much like an atom, but it's a little different. The value in the box can be actually modified atomically. That means that in one single step it will be like changed, and all the other threads who were looking into it, they'll never get a consistent inconsistent view of what's inside the box, right? So mvar is not only just a mutable variable, it's a container for shared state. If you want to share state between multiple threads, then you use an mvar, because you can make sure that the values change atomically, right? So it's actually more than just a box. It's also a blocking primitive. So mvar gives you two operations: put mvar and take mvar. Those are the two basic operations. So a put blocks if the mvar is full already. The box is full, then you cannot put a new value into it, and your thread blocks there. Similarly, if the box is empty and you do take mvar, your thread blocks there. So it's like a single cell queue, a single cell blocking queue, right? That means that you can already see how you can use it for synchronization and locks between different threads, right? So you want to have lock between like a synchronization between two threads. You create a new empty mvar. Then first thread, before the critical section starts, it puts a value in the mvar and then executes the critical section and then takes the value out of the mvar, right? If a second thread arrives at the same critical section, it tries to put the value in the mvar and it blocks there because it's already in use. And then after the first thread is done and it empties the mvar, the second thread can proceed and again take the sort of lock and proceed, right? So you can see how mvars can be used as locks and as synchronization primitives, right? So let's see a bit of actual code. How do you what happens in the connect client call? So there's some setup here, and after that we call read name. So first thing you need is the name of the user, right? Because without a name you can't put the user in the map. So what read name does is that it calls this thing. It calls check add client. Check add client is a call which will atomically check if the username is already present. So if the username is already present, you cannot use that username. Usernames have to be unique. So it must do a check there. And if the check succeeds, it adds the client to that map. But this is a single atomic call. The check and the adding to the map must be done at an atomic way. Otherwise, you would have corruption. So check add client does that atomically. We'll see how it does it. After it does that, then all we need to do is that if it does OK, if OK was nothing, that means that there was already a user with this name. Then we send a message saying the name is in use, use something else, and try to read the name again. And if it succeeded, we get back a client object, and then we can run the client and then talk to the client and do whatever else we want to, right? So let's see how check add client works. So at the very beginning, you have this call modify mvar, right? That is what makes it atomic. So modify mvar is a higher level function composed or created from take mvar and read put mvar, which makes sure that The change to the Mbar is done in one atomic block. So what is inside the Mbar is the client map. Then I take the client map, check if the user asked is already a member, then I can't do anything, I just written the same map. If the user is not there, it's a new user, then I create a new client for that user, insert that client in the map, and then return the client. This whole block is done atomically, and you would never have two users with the same username like in the same map, right? Remove client is pretty simple. After the thing is done, it just modifies the Mvar again to delete the user from the map again. So again, the delete is also atomic, and since both of these calls are using the same Mvar, they will block on each other also, right? So that's it. That's how you do atomic lock sort of thing, synchronized calls between multiple threads and make your code thread safe, right? So you got mutable variables and you got a way to change them atomically, right? So that's it. So we have a way for the user to connect to the server now, and since we spawned a new thread there, the user will stay connected. Now next feature that we have to implement is user to user chat, right? So let's look at the types before we go on, right? So we modified the type now, right? So now the client has a new thing called chan message, right? And there's a new data type here called message, which is just like MSG, a message from user, from a particular user with a particular string. String is the message, right? So we added a new thing called chan. What is it? We'll look into it. And this is some code to just parse the input from the user and let format the input, format the output. So this is pretty trivial, pure functions. So what are chans? And before that, why do we even need chans? So how are we going to implement the user to user messaging is that every user is going to have a chan of the, as we saw in the client, we added a chan. So every client is going to have a chan of its own. A chan is nothing but a unbounded blocking queue. If you are familiar with queues in Java, it's like a linked blocking queue, right? It's unbounded, there's no limit on it, and it blocks when the queue is, it does not, since it's unbounded, it does not block when you try to put, but it blocks when you try to take from an empty chan, right? So every user has a chan now in addition to the handle, right? And sending a message to another user is just taking that message object and putting it into the other user's channel. That's it. And as well as from its channel, so that it can get messages from the user on the terminal or whatever else who are like the actual client, actual user outside the network, as well as they can get messages from the users inside the server, right? So you have to read from both the channel and the handle. So we'll see how that works. So at this point, let's do a demo of what we have. So there it is. I start the server and let's connect to the server. So this code is a little different from the code I've been showing you. So I have to log in by typing this. Right, and then I can log in again with a different name. Right, and let's see if I can message that other guy. That's it. I got the message from that something user. We can also message back. Yep. So the messaging works. Hello. So the messaging works, and we'll see how to implement this using channels. Going back to the code. Okay, so this is the run. Is this working? This is the run client call, which is called after the client has connected and the username has been validated. What does it do? If so, first of all, that syntax over here, I'm not sure if you're familiar with it, but this basically exposes all the fields inside that record to the. It becomes very. They become very like names bind in the rest of the code. So So it gets the server and gets the client, and then forever it loops this code again and again, right? So let's go line by line. First line is try, race, read command, read message. So I told you have to read the message both from the channel and from the handle, right? So that's what the read command will read your things from channel. The read message will read it from, read command reads from the handle, and the read message reads from the channel, and you race them. So now you have two sources of input, right? Now one way to read from both sources of input is sort of like, read one, then read two, read one, read two, read one, read two, like back and forth, right? And then in that case, you cannot have blocking reads, because you have to try to read from first one and then time out, and then read from the second one, then time out, then first one, then second one. Or you could race them. By racing, I mean that you just read from the input source whichever completes first, right? If I get a message first, I read that. If I get a command first, I read that. So I race the read command and read message functions, and whatever I get first is what I use, right? There's a try over there, which is like try catch from Java, except that it returns me a either. So if there is an exception which happens, then I get the left, or if there is no exception, I get the right. So that's it. So that's it. If there's an exception, I just say there's an exception, print it out. If there is a right, then again race returns me another either from left or from right. So if I get a command, now command could be not parsed because parsing could fail. So if parsing fails, I say I could not parse command. If I get an actual command, I handle the command. If I get an actual message, I handle the message, right? So let's look at the read command. Read command is pretty simple. It just reads from the handle, from the client handle, and parses it and then returns it. That's it. Very simple. Read message and write send message are the important ones here. So the channels give you these two primitives. They give you a read chan and a write chan. Read chan is from reading from a chan, and write chan is to write it. And read chan is blocking, as I said, because the channel is empty, it blocks, right? Write chan never blocks. So using these two, we write the handle command and handle message. So handle command is pretty simple. I just look up the list of users. So what I'm handling here is the message. I'm trying to message a different user. So all I do is that I get the list of map of users from the server. Then I look up the username. If the username exists in that map, it does not exist, I just say no such user. If it does exist, then I call send message on by creating a new message to that client, right? So basically, I created a new message object, sent it to that message, the other client's channel, and that other client will receive the message on its channel, and then call handle message, which does nothing but just print it to the handle, right? Just sends it across the network to the client. So that's it. That's how the clients talk. The important piece here is race. How do you read from multiple input? How do you merge multiple inputs together, right? This code is a little difficult to read, but let's go line by line. So first thing you do is that you create an empty Mbar, an empty box, right? Then this line, the bracket fork IO, first fork IO, basically you're launching a new thread to do IOA, the first IO operation, and then you're launching another thread to do second IO operation, right? And then you're blocking on read Mbar. So basically what you're doing is that you say that, okay, go do this first IO operation. If it is done, when it is done, put the value, the result in the Mbar, and then you ask the same thing from the second IO operation, right? And read Mbar will return as soon as a value is put in that box, right? So only one of these two IOs will succeed, and other one will fail. Not fail, but as soon as the first one succeeds, the function returns, right? And that's where the bracket comes in. So bracket is like a try finally again. What it basically does is that after this is basically it has three parts: resource acquisition, resource cleanup, and then actual function, actual operation, right? So as soon as the function returns, it will run the resource cleanup, which will kill the thread. So if the first, doesn't matter which IO operation succeeded, as soon as the function returns, both the IO operation threads are killed, because there's a kill thread there, right? Actually, only one of the threads is killed because one of the operation would have succeeded. The second one would fail, but not fail, but rather be killed, right? So we get we merge the two inputs together into a single uh, box, and then we return the value of that box. It's either A, B, because one of them will succeed, right? So we see the example of Mbar as for inter-thread communication, right? This was an example of Mbar for inter-thread communication. There are more examples of this in the code, but I'll not be able to go through them. We don't have much time. So we are done with user-to-user chat. That's it. We got 2 of the 3 features done, right? Now we have to do the difficult part, chatting in channels. Chatting in channels is more difficult, more complicated than than chatting user to user. User to user is simple. You just send the message to other users' channel. But chatting in channel is different because there are multiple users sending messages to the same channel, and then the channel must sort of send back those messages to all other users subscribed to that channel, right? That means that you must somehow merge a bunch of inputs, like we saw 2 inputs merging together in the previous example. This time you have to merge n inputs together, and then you have to sort of duplicate those n inputs again outwards, right? This is way more difficult way more complicated than using the previous example, right? So you can think of it like this. I could actually race all of these 5 users or 6 users to get their inputs, right? What's wrong with that? What's wrong with that is that you would have to launch 1 thread per user, right? And if you did not notice, there was a bug in the previous race code. The bug is that the second thread, which is killed, may have already done its IO, right? I already got a message from the handle, but it's killed then, and then message is lost forever, right? So it's not atomic, right? Because there is no way to push back messages into the channels or into the handles, right? So we need a way to merge these channels, data channels atomically, right? So that nothing is lost. You only read from one of them, and you never touch any of them else, right? And similarly, you should be able to send messages atomically, like spread them out atomically. The fan in and the fan out must be atomic, right? This is the other side of the channels, where a user is subscribed to multiple channels, right? As well as he has its own channel also to read from, right? So all of these again must be merged atomically and then sent to the guy at the other side of the network, right? So it's difficult to do with Mbars. It's because as we saw in the bracket example, if you do want to do, if you want, basically what would this entail is that you have to read, if you want to use an mchan, you're going to use a chan for each one of them, then you have to have n number of locks and nest them inside each other, right? And then release them in proper fashion. Otherwise you would have like easily run into deadlocks and such, right? That's because locks are not composable. We know this already, that locks, if you have like, you cannot have unbounded number of locks. You cannot say that I have like, I don't know how many locks I have, I'm going to take all of them. That's difficult to do. It's possible, but it's difficult, right? And it's error prone. Second thing, as we saw in the previous example, is that merging is not efficient. You have to launch 1 thread for each merging channel, right? So let's see how we can do this more efficiently, right? We run into software transactional memory. So you may have heard of software transactional memory, or STM as it's called. A lot of languages have STMs these days. Clojure has an STM. Java has an STM using like the multiverse library, right? So STM is like a sort of like a database transaction in your code, right? So what do transactions give? They give you atomicity, consistency, isolation, and durability in case of in databases. So STMs give you the first 3, except durability. Obviously the data goes away when your code shuts down. So it gives you atomicity. That means that an STM, STM transaction is atomic. It's either, it's done in one single go, right? So everything you change in a transaction is visible to the outside world in one single commit. Finally, when it commits, only then it's visible. Till then, while the transaction is running, the other transactions which are running will not be able to see the effect of the same transaction. That's the isolation part. The multiple transactions running on same variables we'll see a snapshot of the variables at the beginning of the transaction, not the state as they change inside the transaction. And it's consistent. The transactions will always take your variables from a valid state to another valid state. You will never be left with some variables have changed, some have not changed, and like or some got like bad values got corrupted or something, right? So transactions are atomic, consistent, and isolated, right? How do you Why do you need STMs? Why do you need transactions? uh, you want to change multiple variables atomically. You want to do that with Mbars, you have to take one lock inside another. It's tricky, right? You want to read from multiple channels efficiently, right? Don't want to launch threads for reading from each channel, right? As well as you want to read from multiple channels atomically. That's the first point. And if there's something which goes wrong in your code, you want to roll back the effects of the transaction, right? You don't want to leave the things sort of like messed up in middle, right? So that's why we use transactions. Let's see this in actual code. So what do? We change we create a new thing called a channel now, right? A channel has a name. It has a TVAR of set of users, which is basically the users who have joined the channel. What is the TVAR? I'll explain. And then it has a TChan of messages, right? So we have moved from chans to TChans, and we have moved from MVARs to TVARs, right? This is the server now. It has been changed to add a map of channels, which is inside a TVAR, right? And the client has been changed to change the client channel from chan to tchan, and now the client also has a map of channels to which the client is subscribed to. There's the map channel name to tchan of message, right? Which is inside a TVAR, because the user subscribes to multiple. You can join multiple channels and leave them and such over time. So you need to change that map all the time, right? So I'll explain all of these in a while. The message the struct has been changed to add new kinds of messages. Now there is a tell, which you use to tell to like send messages to channels. There is join channel, leave channel. There are corresponding replies: tell, reply, joined, and leave. It's called leave because there's already a left in Haskell. So yeah, so this is pretty straightforward. Let's do a demo at this point, right? So the server is running. It disconnected me because I did not respond to the ping. You can look at the ping code in the code. Right. So let me join a channel. Okay, let me join a channel here also. So you see, as soon as the second client joined the channel, the first one got a joined message, like to notify it, right? Now you can talk in the channel. The other client gets a message immediately. So all of the people who are joined the particular channel will get this, can talk among each other using this thing, right? And then we can actually leave the channel. I get left message here. That's it. So we can implement channel to channel, the user to channel communication. Let's quickly go over the STM implementation. So STM first of all comes with a monad of its own. STM does not run in IO monad. It comes with something called the STM monad, which means that you cannot run IO operations in STM monad. You cannot do side effects in STM monad. The type system prevents you from doing IO. The closure STM is not type safe in that similar way. You can do IO in closure STM, and if the STM reruns the transaction or aborts the transaction, the IO is still done. They just say in documentation that you should not do IO in STM. But in Haskell, the type system forces that you cannot do IO in STM, right? Now, that means that transactions can be run multiple times by the runtime, and you would not see any unwanted effects, right? TVAR. TVAR is like Mbar but transactional. It's a transactional variable, right? It gives you a bunch of APIs. You can create a new TVAR. You see that you cannot create a new empty TVAR. TVAR always needs to have a value, right? All of these operations, first of all, except atomically, run in the STM monad. So you can create a you can create a TVAR, you can read a TVAR, you can write a TVAR, and atomically is what converts your STM transaction to a IO, right? You actually need to run something at the end, right? You can't have just a transaction running there and never running it in IO, because the things run always in IO. So atomically will take your STM transaction and run it atomically, as it says, in IO. That's it. You create a STM transaction, you give it to atomically, and it's atomic. Retry is the last thing. Retry is basically so it means that there's something went wrong in my transaction. I want to rerun this, right? So you're running a transaction and see that some value is not what you want it to be to run that transaction. It's a retry. That means that about everything I've done in this transaction, rerun it from the beginning again, right? That's TVAR. Quickly, TChan are channels, transactional channels. They are made of TVARs, and they have this API, new TChan, write and read, and then finally or else, right? So or else is the API for efficient merging. So you can see in the code, in the signature, it just takes one STM operation, second STM operation, and does one of them, whichever finishes first. It's efficient, it does not launch threads, and it's atomic. Only one of them will succeed and other will be as good as never run ever, right? So this is how you get efficient merging in transactional channels. If you have two transactional channels or n transaction channel, doesn't matter. You just try to read from all of them using or else all at once, and only one of them will succeed, and all of the others will be completely untouched, right? This will be atomic and this will be efficient. So let's look at the code quickly. The run client has changed now. So what the very first line is that instead of read commands is now a thread of its own, right? So what I'm doing is that from reading from handle, I launch a thread of its own, right? You can look at read command very quickly. The second code here is basically forever read from the handle and try to parse the command. If the parse succeeds, send the message to the client. That means that what I'm doing is that I'm reading from the handle, parsing the command, pushing it to the client's channel. Remember, each client has a channel of its own, which is now a T-chan. I just send that message to the client, send that message to the client's channel. So now the client doesn't have to handle the handles, right? They don't have to deal with IO, the network operations. All they have to do is that read from a bunch of channels, right? This picture I showed at the beginning, they just have to deal with all of these things on the left now become channels, or even better, they are T-chans, they are transactional channels. So all the user has to do is to merge all of these together, and we already know how to merge transactional channels together. We just called or else over them. So after run, there's this bunch of code to clean up that thread and remove the client, send a leave message. It should not, just basically send a leave message to all the channels that user has joined in. Some cleanup code there. But what's interesting here is the run code. See, run code has been changed to remove race. There is no race anymore. If you see the code here now, what it does is atomically read client's all channels. The client has a map of channels. So I just get the client channel map. Then I fold over the client chan and all the channels, all the channels the client has. All of them together, I just fold over them using or else and retry. That means that try to read from any of these channels. If none of these channels, you can't read for any of these channels, like all of them are like there's no data in there, then you retry. That means that you retry the transaction. And only one of these will succeed because you're using an or else. So you read from exactly one channel atomically, and our other channels are untouched. So don't lose messages. You don't have to create new threads to read from multiple sources. It all works cleanly, right? And all you have to do to make it atomic is put it inside this atomically block. So it magically becomes atomic, right? So rest of the code is same. If you read a message, now you don't have to deal with the network handle stuff. So there's only message left. So if you read a message, just handle the message, right? Now handle message, if you remember the old code, it had a code for handling a message. Let's see how you join a channel, right? So when you join a channel, you get a message called join channel name, right? Now you have to handle the message. So there are a bunch of things which happens here. I've added the comments. You get the user's channels. If the user is not already in the already joined the channel, then you get the server's channel. If the server has that channel present, then add the user to it. Otherwise, create a new channel with the user in that, the or only user as only user in that channel, and then add that user to the server. And then this is the interesting part: the duplicate client tchan and add it to the user. So this is another function that tchans give you, is dup tchan. You can take a transactional channel and make a duplicate of it. That means that whatever comes in the first channel will automatically be forwarded to the second channel, the duplicate channel. And you can duplicate a channel as many times as you want, right? So it's sort of like a fan out, basically, right? So you have one channel and you have data coming in, and you duplicate it n number of times, and all of the duplicates get the same message after, like, it's since the point of duplication, they'll start getting messages, right? So it's like a funnel out. So that's it. That's how the channels work, right? You have the channel has its own tchan, and when a client connects to it, the client duplicates the channel's tchan and keeps a reference to it. So when a channel gets a message from some other user, it's forwarded to all the users who are subscribed to that channel, right? So that's it. You add, you duplicate the channel's chan into a client's channel chan, and then you keep a record of it by putting it in the map, and then tell everyone that you have joined the channel. Now, interesting part is all of this code, all of it is done atomically. Just put atomically at the top, and all of it is done atomically, right? So that means that if two users join at the same time, one of the users will have to retry. If they join the same channel, then they have to retry, because you can't modify the channel's map at the same time, right? So that's it. We're done. We have implemented user to channel messaging, and we saw how this works. The leave and the tell messages would have similar implementations, and they'll all be again atomic. Now let's talk a few minutes about the details of STM. So how STM works, at least in Haskell, is that as you are reading and writing STM variables, it does not actually commit it to the memory. It sort of keeps a journal. It keeps a log of all your STM operations. And at the end of the transaction, it tries to commit it, right? So before committing, it checks that everything is consistent. Like if you wrote something to a variable, someone else also wrote to the variable, and the value has changed in between, then it retries the transaction automatically, right? So it will retry the transaction as many times as it takes to get a consistent, clear transaction, variable changes, right? And when everything is fine, it commits the transaction, right? So this basically means that your STM transaction can run again and again and again. You don't know how many times it's going to run. That means that if you're doing a very computation heavy thing in your transaction, one transaction, which involves, say, a variable A, then if there's a long transaction in the short transaction on the same variable, short transactions will keep interrupting the long transactions again and again and again, and long transaction may never finish, right? So that's why you should never do long running transactions. You should try to keep them as short as possible. This is actually a bad example. You wouldn't write this in actual in actual production code. You wouldn't write this big transactional blocks. You would break it down. So that's one thing. And the second thing is that every write has to verify every read before it, right? When I'm going to write a variable, I have to verify that all the reads which I did to calculate this variable's value are still the same as before, right? That means that the transactions are actually n square in terms of how many reads you do, right? So if you do a lot of reads, your transactions become slower and slower and slower, like by the factor of not factor, but rather n square times. If you do n reads, your if you do 2n reads, your transaction will be 4 times slower, right? So that's one disadvantage of using transactions, right? But obviously there are a lot of advantage if you use it clearly. It leads to very modular and very composable code. You can compose. The good thing about transactions is, unlike locks, they're completely composable. You can take as many transactional STM code and put them together to create bigger transactions, and even bigger transactions from them. So that leads to very modular code, and it is very efficient also in terms of an atomic. Obviously, that's the property of transactions. So that's it. We have implemented all three features. We have gone through the details of these primitives. As there are higher order, higher level primitives also, and you should go to the code and the references if you want to know about them. So let's do a quick review of what we learned in this talk. So um, threads are cheap. Don't be afraid to launch new threads. Launch as many as you want. Doesn't matter. The runtime is very smart. The IO is non-blocking. You don't need event loops. You don't need callbacks, right? You don't need to structure your code in weird ways to do efficient things. Write small components which talk through channels, right? Just break your code in like it's like smaller modular components which don't know about each other. They just don't just know what to read from what channel and what to write from what channel, and just like sort of connected over these channels. That makes your code much modular. That's basically data flow programming, right? And write small functions in STMs and compose them to create bigger functions, right? That gives you very modular code. Structure your programs like assembly lines, which is a very important, very interesting thing which you can do in functional programming. It is difficult to do it in otherwise. Is that you structure your programs like assembly lines. There are processing functions reading and writing from channels, just doing their thing like some sort of forever loop, and the channels are the processing functions are connected with channels like conveyor belts, right? These could be simple channels, or it could be bounded channels. There are bounded channels in Haskell. It could be transactional channels. It could be transactional bounded channels. So you just lay it out your program as an assembly line, and that way you can, it becomes very modular, and you can add new processing functions at different places and such. The channels can be duplicated and merged, at least the transactional ones. That gives you a very good way to construct like very complicated assembly line code, right? So that's all. These are the references you should go through if you want to know, if you want to learn more about them. The Parallel and Concurrent Programming in Haskell by Simon Marlowe, and Real World Haskell, which is sort of outdated, but it's still a pretty good resource, right? So that's where the first thing is where you will find this code. It's a little more fleshed out than these examples. The second is the URL of this presentation itself. That's me on Twitter, and that's me on email. Okay, I think we can take 3 minutes of question. So these are all primitives for one like single machine concurrency. Haskell is not yet very good at distributed machine concurrency. They are still working on it. Probably get there in few years. So these channels are all single machine ones. Yes. Yeah.
Be more like a transactional behaviors exist. But how about in the functional programming? Do Erlang supports a kind of uh, atomic operations in that level, like the Haskell is performing?
So in terms of atomic transactions, there's no sort of intrinsic atomic transactions in the same way that there is there. What you would tend to do is have a process representing your atomic um, data, and you would send a message to it, and it would essentially serialize all the operations in there, and atomicize it, I guess. It does get a little more tricky if you're trying to do something like read a value and then act on that value and write it back. You can do that in an amnesia transaction, but something like ETS doesn't allow that quite the same way.
Yeah, so Erlang doesn't really provide that by default, and it doesn't do that for a very particular reason. And it's the reason that Haskell is currently having difficulty doing distributed computation. Doing atomic operations over a network is effectively impossible to do in a general way. It has to be you choose your constraints and then you implement that yourself. So Erlang is designed natively to exist in a network system, so it doesn't come with those atomic default or atomic guarantees. But you can build them, as was mentioned.
One more question.
Yeah, you talked about transactional channels. So I'm fairly familiar with the co-racing way of doing things. Is it, and we don't talk about transactional channels there. Is it actually doing transactional stuff under the hood, or is this completely different from? So
So core async is a different, like it's actually, if you have seen the core async code and the introduction videos, it trans translates, it's a macro based thing and translates your code. I'm guessing that you're talking about in the go loops, you're like non-blocking, the blocking reads, not the channel, the threaded.
so my point was, you are concerned about um, to read from multiple channels without having to discard or missing some of the messages.
Yeah, so
you needed transactional channels.
so core async runs in two modes. One, you can run it with threads backed by threads, or it could run in sort of like a CSP sort of mode when it like there are multiple processes and they just communicate over channels, but it runs on a single thread, right? So in the second case, in the first case they are like on blocking. They are actually backed by Java's blocking queues, and they would block, right? And probably does poll. I'm not sure how it does it, but probably does time poll or something on multiple channels. If you're running it in like CSP sort of fashion, then it's actually the macros transform whole of your code into a state machine, and it steps through like it automatically knows when a message has been sent and such, and it steps through the state machine. So not exactly same as transaction channels in closure, but you get similar behavior. Yeah. Yeah. I think that's all the time I have. Thank you all.